Greetings to all of you. I'm going to be talking about an exciting and relatively new spectroscopy technique called crossover spectroscopy or intermediate infrared spectroscopy. The last several decades of compositional remote sensing have revealed an enormous amount about the mineralogy and petrology of the moon. And this slide summarizes schematically just a few of those discoveries: the presence and distribution of olivine and pyroxene, the presence and general distribution of anorthite, and the possibility that quartz may be located on certain parts of the moon. But as most of you in the room are probably aware, there is still quite a lot that remains unknown about the basics of lunar mineralogy, including what is the Mg number of olivine and pyroxene? In what olivine and pyroxene enriched rocks is anorthite present on the moon? And is quartz in fact present on the lunar surface? So these are three spectra collected in the laboratory of anorthite, olivine, and pyroxene, spanning the visible through part of the infrared wavelength ranges. And this slide shows how we typically think about this region of the spectrum. We have the visible near infrared on the left-hand side, and we have the mid-infrared on the right-hand side, and a whole lot of nothing in the middle. And we've obviously done quite a lot of great work with this. There are hundreds of thousands of papers I have found on V-near and mid-IR applied to planetary sciences. I'm going to talk today about what's in between these two wavelength ranges. I have called this the crossover range. We also refer to it as the 4 to 8 micron wavelength range. And I'd like to introduce some new terminology: the intermediate infrared, or IMER or IMER, however, whatever sticks best, the intermediate infrared wavelength range. This wavelength range has a lot of exciting potential, as I'll discuss shortly, but there have been no planetary missions that have directly addressed this wavelength range. And by my reckoning, there are fewer than 10 papers on planetary applications of this wavelength range from the last 3 decades. So this plot on the left-hand side shows reflectance spectra of synthetic olivine described by Darby Dyer and others. They range from Mg numbers of 100 on the top in blue to Mg numbers of 0 on the bottom in red. And the most noticeable thing is that there are 2 strong, well-defined spectral bands at 5.6 and 6 microns. And these spectral bands shift systematically to longer wavelengths with increasing iron content. What I then did, the results are published in a paper in GRL, was look at a whole bunch of other olivine separates from terrestrial and extraterrestrial, including lunar and Martian rocks. And these are the results of what we found. On the left-hand side, we have Mg number. On the bottom axis, we have the wave number of the band minimum positions of the 5.6 and 6 micron bands. And what we see is that across this large data set, olivine Mg number forms a strong and distinct trend, meaning that using band minimum positions alone, we can determine olivine Mg number with intermediate infrared spectra within plus or minus 10 mole percent Mg. That was a pretty cool result. And what about pyroxene Mg number? On the left-hand side, we have a plot of synthetic low calcium pyroxenes, originally described by Rachel Kremer. And just as before, we have high Mg on the top, low Mg on the bottom, and we have a strong, well-defined band at 5.2 microns that also shifts to longer wavelengths with increasing iron content. These spectra are synthetic high calcium pyroxenes, wollastonite at 50. They have bands at 5.1 and 5.3 microns, and these also shift to longer wavelengths. When we look at high calcium pyroxenes with a variable calcium content, not depicted here, but in a manuscript that is forthcoming, soon to be submitted, we see that the 5.1 and 5.3 micron bands shift only with respect to Mg number, irrespective of calcium content, and that these trends hold up for natural and synthetic samples of pure pyroxene. So we plot it all up. On the right-hand side, we have the olivine band trend seen before. On the left-hand side, we have the olivine the pyroxene band trends for the 5.1, 5.2, and 5.3 micron bands. And what we see in some is that olivine and pyroxene MG number may be determined with fairly accurately using band position alone with spectra measured in the laboratory. Now, what about the felsic minerals? So anorthite has two subtle but unique bands at 5.4 and 6.2 microns. I have identified these spectral bands in anorthite-rich lunar rocks and in particulate mixtures at abundances as low as 85 weight percent. Now, the really exciting new development is quartz. Quartz has well-defined and unique spectral bands at 5, 5.3, 5.6, 5.9, and 6.2 microns. And these spectral bands are distinct from signatures of other minerals that it would likely be found with, for instance, feldspars. And what all this means is that crossover spectra or intermediate infrared spectra have unique potential for detecting quartz, which has long evaded definitive detection on the lunar surface. This is just the beginning of this work, and I'll leave lots of time for questions. We have a lot more work planned. Myself and my fellow Crocs, the members of the Crossover Consortium, during my NASA postdoctoral fellowship, which I will be starting at Stony Brook in a few months, I plan on investigating lunar rocks and soils in the lab. I plan on determining the effect of optical and physical maturity on intermediate infrared spectral bands. And then finally, my team and I are developing a new spacecraft instrument in this wavelength range in collaboration with engineers. So with that, I will conclude and open myself up to questions or cede my time to the next speaker. Thanks.
Thank you, Chris. We have a few minutes for questions. If anybody, Jacob, is there anybody in the chat who has asked a question?
Not yet, but anybody virtual, please add a question to the chat if you have one.
Okay, we do have someone in the room.
I've got a quick question on how larger particles might alter the way this spectra changes. So you're using between like 5 and 6 microns. And when you bring the range up to about 30 to 100 microns, how different is what you're seeing? And how would that affect what you're looking at?
Okay, thanks for the question. I forgot, so I'm not sure if I annotated on the slide. So most of the particle sizes that we looked at were less than 45 or less than 32 microns. The 5 and 6 microns, that refers to the wavelength of the spectra that we're looking at, not to the particle size. So,
okay,
but as for particle size, which is a really important question, what we see is that these spectral bands are well defined in particle sizes equivalent to what you would see in mature lunar regolith. So in the less than 45 fraction, very strong, well-defined bands. And as you go up toward, I would say at about greater than 125 microns, the spectral bands become a little bit weaker.